welcome to this problem walkthrough. Today, we'll explore a fascinating coding challenge from LeetCode, problem number 1002, titled Find Common Characters. In this problem, we are tasked with identifying all characters that are common across a given array of strings. Stay tuned as we break down the problem and discuss potential solutions. Let's dive in. The problem asks us to find characters that are common to all strings in a given array of words. Each string consists of lowercase English letters, and the solution should return a list of these common characters. Importantly, if a character appears multiple times in each string, it should be included in the output the same number of times. For example, if L appears twice in all strings, it should appear twice in the result. Additionally, the order of characters in the output does not matter. The input is an array of strings, and the output is a list of characters that meet these criteria. Now let's examine an example to better understand the problem. Consider the input array words equals Bella, label, roller. The output for this case is E, L, L. Here's why: the characters E and L are common to all three strings. Furthermore, the character L appears twice in each string, so it is included twice in the output. This demonstrates the rule that duplicate characters must be honored if they appear multiple times in all strings. Looking at another example, if the input is words equals cool, lock, cook, the output is C, O. In this case, the characters C and O are the only ones that are common to all three strings. Both appear exactly once in each string, so they each appear once in the output. This example highlights how the solution respects the frequency of characters across all strings. Here's one more example: words equals hello, world, LeetCode. The output is an empty list. This is because there are no characters that are common to all three strings. When no intersection exists between the sets of characters in the strings, the output should simply be an empty list. Additionally, the constraints for this problem specify that the input array can have up to 100 strings, and each string can be up to 100 characters long, meaning the solution must handle larger inputs efficiently. Finally, let's discuss a few more edge cases. If the input contains strings of different lengths, the solution must still identify the characters common to all strings seamlessly. For example, words equals ABC, ABCD, UB should output a B, since these are the only common characters. Additionally, if the input contains just one string, such as words equals ABC, the output should simply be a list of all its characters, a B, C. These considerations ensure that the solution is robust and handles all possible cases within the given constraints. To tackle this problem, we first consider a brute force approach. The intuition here is straightforward. For each string in the array, we calculate the frequency of each character and then compare these frequencies across all strings to find the common ones. Essentially, if a character appears in every string, we track its occurrence count and include it in our result accordingly. This involves iterating through all characters in each string and performing comparisons for every character. While this approach is simple to conceptualize, it has significant drawbacks. The frequency counting for each string is proportional to the string's length, and the comparison across all strings for 26 lowercase English letters adds overhead. When we combine these steps, the overall time complexity becomes approximately O, n*L, where n is the number of strings and L is the average string length. This can lead to inefficiencies, especially when dealing with larger inputs, as it involves repetitive comparisons for each character, making it less suitable for larger datasets. Now, we move to a more efficient approach using frequency arrays. This method leverages arrays to streamline the process of tracking and comparing character counts. First, for each string, we calculate a frequency array of size 26, where each index corresponds to the number of occurrences of a specific character, A to Z. We also maintain a separate frequency array called common_count, initialized to very large values. This array will store the minimum frequency of each character across all strings. For each string, we update common_count by comparing it with the frequency array of the current string and taking the element-wise minimum. This ensures that at the end of the process, common_count holds the lowest frequency of each character that is common to all strings. Finally, we construct the result by iterating through common_count and including each character the number of times specified by its frequency. This approach eliminates redundant comparisons and processes each string efficiently. The overall time complexity here is O(n*L), which is optimal for this problem. In terms of space complexity, this optimized approach is highly efficient. We only use two arrays of size 26, common_count, which tracks the minimum frequencies, and a temporary frequency array for each string. Since the size of these arrays is fixed and independent of the input size, the space complexity is O(26), which simplifies to O(1) in big O notation. Now, why do we choose this optimized approach over the brute force method? First, it minimizes redundant operations by focusing on character frequencies in a structured way. Second, it leverages the problem's fixed constraint of 26 lowercase English letters, making it highly efficient and scalable. Lastly, the approach is clear and easy to implement, with straightforward array manipulations. The aha moment in this strategy is the realization that we only need to track the minimum frequency of characters across all strings, rather than storing or comparing all occurrences. This insight significantly reduces complexity and ensures correctness. When comparing the two approaches, the trade-offs become clear. The brute force method, while simple to understand, falls short when handling larger strings or arrays due to its inefficiency in performing repetitive comparisons. On the other hand, the optimized approach using frequency arrays is more efficient, scales better for larger inputs, and avoids unnecessary computations. This makes it the clear choice for this problem. In summary, the optimized approach not only ensures correctness but also achieves clarity and efficiency, making it the ideal solution for find common characters within the given constraints. By focusing on the core insight of tracking minimum frequencies, this method elegantly balances performance and simplicity, providing a robust way to solve the problem efficiently. In this problem, we are given an array of strings, and our goal is to find the characters that are common to all the strings, including their minimum frequency, and return a list of these characters. To solve this, we'll use a systematic approach. First, we initialize our data structures. A key optimization here is to use a fixed size list of 26 elements, one for each lowercase letter of the alphabet. This avoids the overhead of dictionary lookups and ensures efficient space usage. We create an array, min_frequency, initialized with infinity for each element. This array will help us track the minimum frequency of each character across all the strings. Now, with the initial setup in place, we can begin processing each string to determine its character frequencies and update the global min_frequency accordingly. To complete the process, we then construct the result by iterating over the min_frequency array. For each character index where the value is greater than 0, we know that the character is common to all strings. By converting the index back to the corresponding character using CHR, we can append it to our result list. Additionally, we append it multiple times based on its frequency stored in min_frequency. This ensures that the result respects the minimum occurrence of each character across all strings. Finally, we return the constructed result list. The approach is efficient because we use arrays instead of dictionaries for frequency tracking, which saves space and speeds up lookups. By focusing on minimum frequencies, we ensure that the solution accurately represents only the characters shared by all strings. It's important to consider edge cases to ensure the algorithm works robustly. For example, if the input words array is empty, we should immediately return an empty list because there are no strings to compare. Similarly, if any string in the array is empty, the result must also be empty since no character can be common. Another critical aspect is handling strings with repeated characters. The algorithm must carefully count these repetitions to avoid overestimating their frequency. The data structures used here are straightforward but effective. The min_frequency array tracks the minimum frequency of each character across all strings, while the frequent array is reset for each string to capture its individual character frequencies. Finally, the result list accumulates the common characters to be returned, ensuring the output is both accurate and efficient. The time complexity of this algorithm is determined by the steps involved. Counting character frequencies for each string is proportional to the string's length, O(L). Updating the min_frequency array involves a fixed number of operations, one for each of the 26 lowercase letters, making it O(1) per string. Constructing the result also involves iterating through the 26 characters and appending them based on their frequency, which is again O(1) for each character. Combining these steps, the total complexity is O, n asterisk L, where n is the number of strings and L is the average string length. In terms of space complexity, the algorithm requires fixed arrays of size 26 for min_frequency and frequency, which means O1, auxiliary space. The result list, however, uses space proportional to the size of the output, which depends on the input. Overall, this makes it a very space-efficient solution. Let's walk through an example to see how the algorithm works in practice. Consider the input words equals, Bella, label, roller. First, we initialize the min_frequency array with infinity for all 26 elements, representing the minimum frequency of each character. Then, we process the first string, Bella. We calculate the frequency of each character and store it in the frequent array. For instance, the frequency of B is 1, E is 1, and L is 2. We then update min_frequency to match these values since this is the first string. Next, we move to the second string, label, and repeat the process. We calculate the frequency of each character and update min_frequency by taking the minimum of its current value and the frequency in this string. Finally, we process roller in the same way, ensuring that min_frequency reflects the lowest frequency of each character across all strings. Once all strings have been processed, we construct the result by traversing the min_frequency array. For each character index where the value is greater than 0, we append the corresponding character to the result list multiple times based on its frequency. In our example, the characters E and L appear in all three strings, with L having a minimum frequency of 2. Therefore, the final result is E, L, L. This output accurately represents the characters that are common to all strings and respects their minimum frequencies. The algorithm efficiently handles the input and produces the correct result by leveraging fixed-size arrays for frequency tracking and focusing on minimum values to ensure correctness. This Python solution implements the problem of finding common characters across all strings in an array words while considering their minimum frequency. The algorithm begins by importing the counter class from the collections module. The counter class allows us to efficiently compute and manage character frequencies in strings. The commonChars function first initializes a frequency counter for the characters in the first string of the words array. This serves as the baseline for common character counts. Next, the function iterates over the remaining strings in the array, updating the frequency counts by taking the minimum frequency for each character. This is achieved by calculating the intersection of the current counts with the counts of the characters in the current string. If a character is not present in the current word, its count in the common counter is set to 0. Finally, the function constructs the result list based on the final frequencies in the common_count dictionary. For each character, the result list is extended with the character repeated by its frequency. This approach ensures correctness while maintaining efficiency. The use of counters simplifies frequency calculations, and the algorithm handles edge cases like empty strings or characters not appearing in all strings. The overall time complexity is approximately O(n*)m, where n is the number of strings and m is the average length of a string. Here, we begin by importing the necessary libraries and defining our class and method. The goal is to identify the characters that are common across all the words in the given array. To do this, we initialize an array called commonCount to keep track of the minimum frequency of each letter across all words. This array is filled with the maximum possible value initially, ensuring that any comparison will reduce it to the actual frequency. Next, we loop through each word in the input array. For each word, we calculate the frequency of its characters using another array called currentCount. Each character in the word increments the corresponding index in currentCount. After computing this, we update commonCount by taking the minimum of the existing value in commonCount and currentCount for each character index. This ensures that commonCount ultimately reflects the lowest frequency of each character across all words processed so far. Finally, we use the commonCount array to construct our result. For each character, if its frequency in commonCount is greater than 0, we add that character to the result list the specified number of times. This ensures that only the characters appearing in all words and in the correct frequency are included. At the end, we simply return the result list, which contains all the common characters. This approach efficiently ensures that we account for both the presence and the frequency of characters across all input words. To solve this problem, we start by analyzing the input array of words. In this example, the input is Bella, label, roller. The first step is to initialize a common underscore count dictionary using the character counts from the first word, Bella. By using Python's counter, we determine that Bella contains 1B, 1E, 2 Ls, and 1 A. This forms our initial common underscore count. Next, we process the second word, label. For this word, we create a new current underscore count dictionary that tracks its character frequencies, 1L, 1A, 1B, and 1E. To update common underscore count, we compare the counts of each character in both dictionaries and keep the minimum count for each character. For example, B and E both remain with a count of 1, L stays at 2, and A remains at 1. This gives us an updated common underscore count of L, 2, B, 1, E, 1, 1 after processing the first two words. Now, we move on to the third word, roller. Again, we create a current underscore count dictionary for this word, which contains 2 Rs, 1 O, 2 Ls, and 1 E. We then update common underscore count by comparing and taking the minimum counts. For B and A, their counts drop to 0 since they do not appear in roller, so they are effectively removed from the dictionary. E remains with a count of 1, and L stays at 2. This final common underscore count becomes L, 2, E, 1. From here, we construct the result list by expanding the characters in common underscore count based on their frequencies. So, L appears twice, and E appears once, resulting in the output, L, L, E. In this second example, the input is cool, lock, cook. We start by initializing common underscore count with the character counts of the first word, cool. Using counter, we find that cool contains 1 C, 2 O's, and 1 L. This becomes our initial common underscore count. Next, we process the second word, lock. For this word, the current underscore count dictionary shows 1 L, 1 O, 1 C, and 1 K. To update common underscore count, we take the minimum frequency of each character between the two dictionaries. For C, O, and L, their counts remain at 1, while K is not present in the first word, so it is excluded. The updated common underscore count becomes C, 1, O, 1, L, 1. Next, we process the third word, cook. The current underscore count dictionary for this word is created, showing 1 C, 2 O's, and 1 K. We update common underscore count by taking the minimum frequency of each character. For C and O, their counts remain at 1, but L drops to 0 since it does not appear in cook, so it is removed. The updated common underscore count becomes C, 1, O, 1. Finally, we construct the result list by expanding the characters in common underscore count based on their frequencies. This results in C, O as the output for this example. In this final example, the input is ABC, def, GSI. We begin by initializing common underscore count with the character counts of the first word, ABC. Using counter, we find that ABC contains 1A, 1B, and 1C. Next, we process the second word, def. The current underscore count dictionary for this word shows 1D, 1E, and 1F. When updating common underscore count, we see that none of the characters in ABC appear in def. As a result, the counts for F, B, and C drop to 0, leaving us with an empty common underscore count. Lastly, we consider the third word, GHI. Since common underscore count is already empty, no updates are needed. The result list is constructed as empty, leading to the output. To analyze the time complexity of this solution, we start by considering the initialization of the counter for the first word in the list. This operation requires iterating through the characters of the word to calculate their frequencies, which takes M time, where M is the length of the first word. Next, we process the remaining words in the list. For each word, we create a counter to calculate its character frequencies, which also takes M, where M now represents the average length of the words. Then, to find the common characters, we intersect the frequency counts with the current common underscore count. This step involves iterating over the unique characters in common underscore count, which are at most K in number. For each character, we compute the minimum frequency between the two counters, and since this is a constant time operation, the overall complexity for this step is K. Combining these steps, processing each of the N1 remaining words requires M plus K time, making this the dominant term in our time complexity analysis. Once all the words are processed, we move on to constructing the result list from the final common underscore count. Here, we iterate over the unique characters in common underscore count, which are at most k. For each character, we extend the result list by its frequency, meaning we append the character multiple times equal to its count. In the worst case, this could involve appending up to the total character count across all words, which is proportional to O(m*k). However, since we already determined that k is constant, the dominant term of the time complexity remains the iteration through the words and the intersection of their frequencies. Therefore, combining all steps, the overall time complexity of the solution is O(n*m plus k). Given that k is constant, the time complexity simplifies to O(n*m), where n is the number of words and m is the average word length. This makes the algorithm efficient and scalable for larger inputs. When analyzing space complexity, we begin with the common underscore count object. This counter stores the frequency counts of at most k unique characters, which requires k space. Similarly, for each word, we create a temporary counter object, current underscore count, to store its frequency counts, which also requires k space. Additionally, the result list stores the common characters, with each character repeated according to its frequency in common underscore count. In the worst case, the size of this list could be proportional to the total number of characters in the smallest word, or O(m). Since the storage needed for the counter objects dominates the space usage and k is constant, the overall space complexity simplifies to O(m). This ensures that the algorithm uses memory efficiently, even for larger inputs. To compare with a brute force approach, consider iterating through all possible characters from A to Z and checking their frequency for each word. This approach would result in a time complexity of O(n*k*m), where k represents the number of unique characters, which is 26 for lowercase English letters. In contrast, the optimized solution leverages counter objects to efficiently compute the minimum frequencies of characters across words. By focusing only on the characters that are present in the words, the dependence on k is effectively eliminated, reducing the time complexity to O(n*m). This improvement makes the optimized solution significantly faster and more memory efficient, especially for larger inputs, as it avoids unnecessary computations and takes advantage of the constant size of the character set. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, when all words are identical, the frequency counts in common underscore count remain unchanged throughout the iterations, and each word is processed with minimal effort. In this scenario, the complexity remains O(n*m). In the average case, where the words have some overlap in characters, the algorithm efficiently updates common underscore count to reflect the minimum frequencies, with a complexity of O(n*m). In the worst case, when the words share no common characters, the common underscore count requires frequent updates as characters are removed, but the complexity still remains O(n*m). This consistency in time complexity across all cases highlights the efficiency of the solution, which effectively uses counter operations and the constant size of the character set to handle all scenarios with the same level of performance. When solving this problem, there are a few common mistakes to be mindful of. First, not accounting for edge cases can cause your solution to fail unexpectedly. These edge cases include scenarios like an empty list of words, or a list containing empty strings mixed with other inputs. For example, if words is an empty array or contains strings like alongside ABC, you need to handle these explicitly to avoid errors. Next, incorrect character frequency representation is another frequent issue. Using the wrong data structure, such as a simple list instead of a dictionary or a specialized tool like collections accounter in Python, can lead to inefficiencies and bugs, especially when working with large datasets. Finally, one of the biggest pitfalls is overlapping nested loops without optimization. A brute force approach with multiple nested loops can quickly escalate to O(n²k) complexity, where n is the number of words and k is the average string length. This can be prohibitively slow for larger inputs. Instead, look for ways to pre-process or optimize for efficiency. Another critical mistake to avoid is ignoring case sensitivity or non-alphabet characters. For instance, assuming all characters are lowercase or purely alphabetic can lead to incorrect results when inputs contain uppercase letters or symbols. It's vital to explicitly check and handle these cases, and if you're in an interview setting, always clarify constraints with the interviewer beforehand. Additionally, hard-coding input sizes or constraints is a common pitfall. Making assumptions about the size of the words list or the length of individual strings, without adhering to the problem's constraints, can result in runtime errors, especially on edge cases. For example, constraints like 1 equals len, words, equals 10 to the power of 4 must be respected. Always validate your solution against these constraints to ensure robustness. To excel in interviews involving this problem, there are some key insights to keep in mind. Pre-processing the input is often crucial. By transforming the input into a more manageable format, such as a sorted tuple of characters or a frequency map, you can simplify your solution and improve efficiency. Optimizing for both space and time complexity is another important goal. While a brute force solution may be acceptable initially, interviewers will look for how you refine your approach. For example, using hashable representations of character frequencies can enable faster lookups. Communication is also key. Ask questions early to clarify constraints like case sensitivity, handling of special characters, and the maximum input size. Finally, leveraging hashing techniques can provide significant benefits. Many problems involving comparisons or grouping can be solved more efficiently by storing pre-computed values in a hash map, reducing redundant calculations. If you're preparing for interviews, consider exploring related problems like group anagrams, valid anagram, or find all anagrams in a string, as they often share similar concepts and techniques. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is the sorted string representation approach. Here, you sort each string in words and use the sorted version as a key in a hash map. This method simplifies implementation but comes with a trade-off. Sorting each string takes k*log k time, which can become a bottleneck for very long strings. Another approach is to use a character frequency count, where you represent the frequency of characters as a tuple, such as a fixed-size array for lowercase English letters. This allows for faster lookups and uses constant space for frequency representation, though it does require some pre-processing. Finally, you might consider using a tree or prefix tree to organize strings by shared prefixes. This can reduce redundant comparisons and improve efficiency for certain patterns, but it introduces additional space complexity and can be more challenging to implement. Each of these methods has its strengths and weaknesses, so the best choice will depend on the specific constraints and requirements of the problem. Congratulations on completing this walkthrough. In summary, we tackled the problem find common characters and explored the brute force approach. Remember, understanding frequency mapping and optimization techniques is crucial for string manipulation problems. Thank you for watching, and don't forget to like, subscribe, and share. See you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!